All right. Hello, everyone. Welcome to today's installment of the Corundum developer meeting. This one's the one for March. Thanks for tuning in. All right. So for the agenda, I just have announcements and status updates for today, but it's been a whole month, so I actually have a number of status updates to go over. All right. So real quick, first with the meeting scheduling. The next developer meeting will be on April 3rd at 9 a.m. and 9 p.m. Nobody showed up to the last 9 p.m. slot. So if that's not useful for people, then I'll stop holding that one. So I'm going to do at least another one tonight. But if nobody shows up to that one, maybe I'll cut it. We'll see. Last month was the first one, so if people didn't know about it, that's fine. So I'll give people another chance. Um, Anyway, the Chrono developer meetings are going to be once per month, and the Switch developer meetings are going to be twice per month, but offset by a week. I have a Google Calendar that's linked on the wiki page, so if you go to the GitHub wiki, you can find a link to that and add it to your calendar, so you have all the nice events in the correct time zone and whatnot. Hopefully. Also, the next Switch developer meeting will be next week on March 13th. So if you want to hear about what Colors has been working on, you can tune in then. All right, so moving on to the status update summary for Corundum. Been working on a bunch of stuff. So there's a couple other things with the Mac and Phi components and the PTP subsystem. I got truncated timestamps working, so that saves a little bit of block RAM and also improves the timestamp resolution at 100 gig, which is potentially useful on the Xilinx devices. And I've been doing a whole bunch of work on the scheduler, and as part of that, I think I've got the design to the point where we can support multiple ports per interface and have that exposed at the driver level as actually separate network devices. So that's been implemented, and it seems to be working the way it's supposed to. And then I've been doing a bunch of other, modifications and improvements to the scheduler in preparation for converting it to support, multiple ports and multiple traffic classes inside of the same scheduler instance. So I'll talk about that a little bit. And then I've also come up with a couple of possible architectural changes to help improve the performance of the design overall. So I'll talk about that, and then the latest status on the application section pass through as well. All right, so let's get into it here. For the Mac and Phi, the main thing that I did is I modified how they're handling the PTP timestamping. So previously, the PTP clock period was passed in as a parameter, which means it was fixed at synthesis time. So if you reconfigure the Mac to run at different rates, then it's not going to be using the correct correction value at all the rates. So instead, I set it up to extract the PTP period from the PTP time, and then it'll use that instead of the parameter. So now if you change the clock speed or you change the data rate, then the Mac will figure it out and use the correct value when it's um, let's see. It needs to do this because at the 10 gig and 25 gig, it can start a packet in either lane 0 or lane 4, so it has to offset by half of a clock period in the lane 4 start position. So that's the only thing it uses it for. Um, but yeah, this I don't think it really changes the footprint of the logic very much. Might make it a little bit bigger, a couple more flops, but it makes the timestamping a little bit more accurate. All right, so I also made a few other changes to the PTP subsystem. The first one is I adjusted the PTP hardware clock module to wrap at a slightly different point. So with the time distribution messages that carry the information about the PTP time, they contain a relative to time of day offset for 2 seconds, right? The current second and then either the previous second or the next second, depending. So previously it switched basically the middle of the current second, but in general, you're going to be working with captured timestamps that are in the past. So if you switch towards the end of the current second, then you'll get a better reconstruction window. So by looking at just a couple of MSBs um, instead of what I was doing before, right? If you look for all three MSBs set, then you'll get a wrap point at about 940 milliseconds. So that means you could reconstruct about 940 milliseconds in the past and about 60 milliseconds in the future, which I think is pretty reasonable. And then I also added a relative to time of day conversion module that takes in a 48-bit truncated relative timestamp and converts it to a 96-bit time of day timestamp. Basically, just applies both of the offsets from the messages and then figures out which one's the correct one. And the idea here is it saves logic resources when handling the timestamps because now instead of having to put 96-bit timestamps on all the FIFOs, well, now you can just put 48-bit timestamps in the FIFOs. So it should save a few block RAM resources and potentially a few other things. So in terms of what has happened on the Corundum end, I've updated the design to support 32.16 truncated timestamps. So it's half the size. And I've also added the PTP timestamp format parameter, which allows you to select which format to use. So you can either use the full 96-bit timestamps, or you can use the truncated timestamps, depending on what the Macs support. So all the Xilinx designs I switched to using the truncated timestamps, and the Intel designs that use the soft Macs I also switched. The E-tile designs on for Intel parts, those have not been switched yet because I'm not sure what the restrictions are on the PTP clock inputs and how those things work. So those might need to be left alone, but we'll see. And there's also some weird issues with the PTP support on the E-tile anyway. So yeah, that'll be a project for a different day to get the kinks worked out of that. One interesting thing to note about the Xilinx devices is that I had to switch the CMAC instances to the relative clocking mode instead of the absolute clocking mode. And that means, and the upshot of that is that all of their PTP timestamp ports are 80 bits instead of 96 bits. So in the time of day mode, you have to drop the fractional nanosecond field. But if you switch it to relative mode, well, then you actually have to pass through the fractional nanosecond field. So that means that in the relative mode, we actually get the full resolution timestamps out of the CMAC. So that's a pretty significant improvement. And I also went ahead and added the fractional nanosecond field to the completion records. Unfortunately, Linux doesn't support fractional nanoseconds, only integer nanoseconds. So it doesn't change anything about how PTP4L works, but potentially that data is available for other PTP implementations if you need something super high resolution. I think White Rabbit needs the high resolution timestamps, so potentially it'll be useful there. Although I guess with White Rabbit is a question of where you're going to close the loop. Is it done in the host, or is it going to be done in the hardware? Not sure, but either way, we need that resolution, I think. So it's there.
Yeah,
All
for the
right.
PTP, it's in the host, I think. But okay.
Yeah, for PTP, it's in the host.
Yeah, I think so. For the Switch,
Okay.
yes.
Okay. So, well, yeah, whatever we end up doing, we'll have the high resolution timestamps for that. So, yeah, so I guess with White Rabbit, there's kind of two levels to it, right? You have to do the kind of the low level phase synchronization with the PLL,
Yeah,
digital PLL, and then you also have the you basically have to set the clock with PTP.
yeah, that's it.
Yeah. Well, there's probably a few different ways of implementing that, so we can circle back to that when we're getting closer to actually getting White Rabbit running on this.
Sure.
Anyway,
Mhm.
so after switching over to the relative for the truncated relative timestamps, I took a look at the resource counts for a couple of the modules involved just to see what the savings might look like. So if you look at some of the individual modules, the savings are actually decent. So like for the leaf clocks, you get about a 20% savings for both LUTs and flip-flops by not having to compute the time of day timestamp. So that's pretty good. The timestamp conversion module is also relatively small, only about 70 LUTs and 200 flip-flops. The 25 gig Mac, you save a handful of flip-flops primarily. You don't save all that many LUTs. The main difference in the Mac is you don't need to deal with the seconds field increment. So I think that's where you're mainly getting the savings from there. But if you look at larger designs, you don't necessarily save much. So I'm not exactly sure why. I think this is kind of a side effect of the tool, build process, because there seems to be, if you build a design like 2 or 3 times, you get different resource counts. So um, the for the single port designs, I think we're kind of in the noise in terms of the actual LUT count and register count values. And as you save a few flip-flops, for the 100 gig design, it seems like it actually got a little bit bigger. But the main thing that you do save is a couple of ultraram blocks, which makes sense because in the receive FIFO, you're making that narrower by 48 bits. So that definitely knocks off a few ultrarams. But for this design here, where we have 4 ports, there actually is a relatively significant savings of about 2,000 LUTs and about 6,000 flip-flops. So, definitely some improvements by lopping off those extra timestamp bits that we can reconstruct. So this all works in hardware, and this is all live on my development repository. And this hopefully will be getting pushed up to the main upstream repository soon. All right, so moving on to what I've been working on the scheduler side. In order to support multiple ports per interface, what I need to do is set up, or multiple ports and multiple traffic classes. What I want to do is update the scheduler to support all of that internally. So you don't need, multiple scheduler instances. You can just have one scheduler that does everything, basically. So it needs to be able to, per priority and per port, keep track of a round robin schedule. And then it has to implement both priority and round robin across all of those channels, right? Priority within the traffic classes or between the traffic classes on one port, and then round robin across the ports, so you can make sure that every port gets a chance to actually send something. Right, and then we need internal flow control to make sure that you're not going to have a significant amount of headline blocking. So you don't want, a high priority traffic class to be stuck behind a low priority traffic class because you don't have space in the transmit FIFOs. And you also don't want to have, one port backing everything up and then the other ports can't send data. So it's quite important to not start transmit operations if you don't have space in the transmit FIFOs. So I've been working on a couple different things here. One of them is to get this internal flow control working, and the other one is to get the scheduler to a point where it can support multiple ports and multiple priorities inside the scheduler. All right, so I guess I talked about this a little bit here. The new schedule that I'm working on, it needs to do round robin across the ports, priority scheduling across the TCs on each port, so you can have high priority and low priority traffic classes, and then round robin on all the scheduled queues inside of each traffic class. And then the queues, the idea is you'll be able to schedule those on multiple ports if you want to, but only on one TC per port to simplify things a little bit. And then we need internal flow control to manage the buffer space. So operations, they can only start if you have at least one MTU of available buffer space. And this will be done on a scheduler channel basis. So we're going to have one flow control channel per TC per port. So if you have, say, 2 ports and 4 TCs, you would have 8 channels. Each one is independently going to be managing the flow control state. And then the flow control, it's going to be tracked per channel. And you can set, on a per channel basis, how much of the transmit buffer it's allowed to use. That's the idea. So the internal flow control, it needs to enforce both a byte limit and possibly a packet limit. But the problem is we don't know the size of a packet until we've read the descriptor and we're actually starting the transmit process. So we have to assume that it's going to be an MTU packet because, that's the only reasonable assumption that you can make at that point. But if you always reserve an MTU size block, it's going to be inefficient. So there has to be some way of kind of recovering that extra reservation if, once you know the packet size, so you can actually use the full buffer capacity in the hardware. So the high level idea is that this kind of works like a credit card. If you've ever pumped gas before, the way it works is you have a credit limit that you can't exceed. That's in terms of bytes in the buffer. So you place a hold for an MTU size block, and that the holds cannot exceed the credit limit. Once you've actually started the transmit process and you know how big the packet is, you can swap the hold for a charge of the actual amount. And then when the operation completes, you can pay off the amount. So, and this whole time you have to make sure you don't go over the credit limit. Unfortunately, it's relatively straightforward, but it's not particularly accurate, right? There's no late fees, no interest, no miles, no rewards, you know, but it does kind of get the point across. All right, so the first idea I had for implementing this is scaling. So before the transmit operation starts, you just track the packet count. After the transmit starts, you track the packet count and the byte count because you know how big the packets are. So the question is, how do you relate the number of packets before you know the packet size to the byte count? Um, so you could like increment or decrement by the MTU, one packet at a time. You could also like scale and shift the packet count. Um, so the advantage of shifting and scaling the packet count means that this is kind of a relatively clean operation because you can change the MTU and buffer size whenever you want, and the flow control will just kind of work itself out. But the disadvantage is this is possibly a complex calculation, especially if you want to do all this every time you're trying to send a packet, right? If you make this a very tight loop, having to do, all of these, multiplications and all of this math, that doesn't necessarily work very well in terms of timing and area and whatnot. So I kind of went back to the drawing board and came up with a couple of ideas. The second idea I had was um, what I was calling buffer borrowing. So the idea is that if you have a buffer of so tracking packet counts is easy. So if we know we can send 5 packets, then we can send 5 packets. Um, if we have to do this complicated calculation every single time we want to send a packet, then that's potentially going to be more problematic. So let's say we have a buffer of n bytes. N over the MTU size gives you k packets. Well, you can immediately send k packets. And then as we start sending those packets, we look at the packet size, or the MTU minus the packet size, and we can keep a running total of that. When that crosses an MTU, okay, well now we can send another packet. So everything is just in terms of onesie, twosie, how many packets can we send? So the credit check is very simple. It's just, hey, do we have at least one packet credit? Okay, then we can send a packet. The disadvantage is that at some point, well, we have to recover these, as operations complete, we have to recover these extra credits that we generated at some point, and I'm not really sure the best way of doing that. And that could potentially introduce a lot of corner cases that would be difficult to work out. This is not like a nice straightforward thing where you just have some, input values that you can use to calculate how many credits you can send. It's got kind of this internal state. And if you don't handle that correctly, then you can get the credit tracking stuck, and that's something you want to avoid. So the next plan I came up with is what I was calling split credit generation. So the idea is that you split off the credit generation from the actual transmit process. So in the previous one here, we just have, how many packets can we send, and you're just looking at that directly. In this case, we don't have a number for how many packets we can send necessarily, but we're generating flow control credits in one process, and then another process we're consuming them. So the process that consumes them, that's very simple because we're just looking at the credit count. But the process that computes them can potentially be a little bit more complicated. And since that's separate, we don't have to worry as much about the critical path. So the idea I came up with this one originally is to do something kind of iterative where you start out with a buffer size value. It starts at 0, and a buffer limit value, which is specified as how big the buffer can be, or how many bytes you're allowed to use. And then every clock cycle, what you do is you take the buffer size plus the MTU and you see if that's less than the buffer limit. If it is, then you increment the buffer size by the MTU size and you generate flow control credit. And then that goes off to the other process that's actually going to be sending the packets. If you have a credit, okay, then you can send a packet. But these credits can accumulate. So we can run this process until we've run out of available buffer space, and then we have a bunch of flow control credits that we can spend. And then as packets complete, we can then free up MTU minus packet size. And if we're sending a bunch of small packets, this will add up to an MTU after a couple packets, and then we can generate another flow control credit, send another packet. So the advantage of this is it's relatively simple, and you can set the buffer size and MTU size in bytes directly, and you can change the buffer size whenever you want. You don't need to calculate scaling values and things like that. But the disadvantage is changing the MTU size is potentially problematic because since we're incrementing and decrementing by the MTU, you can end up in a state where the buffer size has some credits stuck in it that you can't really recover. So I was thinking about how to do this, and it just seems like it opens up the potential for some weird corner cases that would be hard to handle. Because basically you have to drain all the flow control credits before you can change the MTU size, and it's unclear if that would be opening the door to lots of weird corner cases. But then I thought of, wait, I could take this first idea and the last idea and kind of combine them together. So this is what I actually ended up implementing, where we do both scaling and the split credit generation. So the idea is pretty straightforward. We do the first one to figure out how much buffer space we have available, and then basically you just figure out how many MTU size packets you can fit in there. So the first thing I realized is that, well, actually an 8x8 multiply in LUTs is not bad. So what?
Yeah, I know. Yeah. Discovery.
What did you want to say? Okay. I thought somebody had a comment here. Yeah, so the first thing I realized is that an 8x8 multiply in LUTs is actually not too bad. Originally, I'm like, oh, geez, if there's a multiply in there, that's going to have to go in a DSP slice, and that could require a lot more pipelining or something. But for a large multiply like 12 or 16 bits or something, yeah, you probably need a DSP slice. But for 8x8, it's actually not too bad. But then what about, if we want to compute batches of credits instead of just one at a time, if you're going to do something like buffer available over MTU size to get how many credits, it seems like that should require division, which is even worse than multiplication. But then I realized, actually, not necessarily, because with flow control, the thing is you don't actually have to be perfect. You just have to basically come up with a bound, right? If you don't release quite enough flow control credits, you're not going to go, you're maybe not going to be as efficient as you could be, but you're not going to overrun the size of the buffer. And if we're releasing a handful of credits, in one shot, that's going to be better than just releasing one credit at a time. So what we can do instead is we can approximate dividing by using, bit shifts and comparisons. So the method I came up with is, you have the buffer limit, the packet limit, and the data budget that you can set. So the buffer limit is how big the buffer size is in bytes. The packet limit is how many packets you're going to be allowed to send, and then the data budget is basically the MTU size, how much you can send at each transmit operation. So what you can do is compute the total bytes as the byte count that you've accumulated from all of the active transmit operations, plus the fetch count times the data budget. So how many packets are being fetched, but you don't know the size yet, times the data budget. That gives you the total bytes. Then you take the buffer limit minus the total bytes and you compare that to data budget, right? If it's at least the data budget, then you can generate one credit. But if you shift the data budget by one and do the same comparison, well, now we know we can send two, and you can do it again, shifting by two for 4 credits and again for 8 credits. So instead of doing a division, we can do 3 or 4 magnitude compares with bit shifts, and bit shifts are free. They're free on FPGAs. So this will allow you to, with a relatively small footprint and pretty good timing performance, compute how many credits you might be able to get or how many packets you might be able to fit into the available buffer size. So the advantage of this is it's pipelinable, because since we're splitting the credit generation, we don't need to get this to fit inside of one clock cycle. It's amenable to distributed RAM because, well, since we're computing in batches instead of just one at a time, we don't need to update this every clock cycle, right? So that helps the pipelining. That also helps with distributed RAM because we can share this logic across all of the scheduler channels. We don't need to replicate this on every single channel. So we can have distributed RAM to store, the buffer limit, packet limit, the various counters, and then update this incrementally. And we can also change all the settings freely, right? You can change the data budget, the buffer limit, packet limit, and it doesn't break anything when you do that. So once I came up with this idea, I'm like, okay, I think this is going to work. So I went ahead and I implemented a single channel version of that in the hardware. And I also set it up in a way that we can use distributed RAM. It's not using it yet, but it's organized such that that should be pretty straightforward. And I've gone ahead and tested it in the hardware. I did have to bump up the transmit FIFO size to match the transmit RAM size, because the flow control credit buffer limit is set based on the transmit FIFO size. So if the transmit FIFO is too small, then it won't actually, then you won't get very good performance because it can't start very many transmit operations. It can't do much in parallel. So the to-do for this is to implement the multi-channel version, but the single channel version does work, and that's up in my development repository right now, so people can test that. All right, so now that I had that working, then I went and took a look at the device driver, because now that we can actually have multiple schedulers running and not interfering with each other due to the flow control credits, what we can do is actually isolate the individual ports and expose them as separate network interfaces at the operating system level. So I added support to the driver to basically manage the schedulers better, to deal with allocating and configuring the multiple scheduler channels and associating them with the net devices and whatnot. And I updated the device driver to register net devices for all of the ports that the design is configured with. So I tested it with a 2-interface 4-port 25D design, and all the ports worked. You could use them all at the same time, and it seems to work fine. I also updated the test bench driver model to do all the same things as a device driver. So in the test bench, you can do the same thing. You can turn on all the ports, register multiple net devices, and everything is handled correctly. I also updated the dumping utility to remove the port select option, and it just dumps all of the port status as part of the selected interface. One thing that I do need to do is go through and actually update a lot of the 25D designs to turn on all the ports, so we can actually take advantage of this. And I'm also going to consider dropping all the interface counts to 1, because with other improvements to the interface components and the scheduler, and I don't think there's really a compelling reason to have multiple interfaces. It makes sense just to use one interface and amortize that logic across a bunch of ports. And this is what it looks like with the driver modified for this, with both just the IP route tools. You can see all the ports listed, and then also the devlink utility as well lists all the ports. So this was the design with 2 interfaces. So previously, you just see basically port 0 and port 4, but with this new support, well, we see all of the individual ports. So that's pretty good. Works. And then moving back to the scheduler, I started chipping away at some other internal components on the scheduler to try to get things into a good spot for converting to the multiple channel version. So one thing that I did is I applied a similar technique that I use on the queue management logic, where we have these basically encoded commands that are used to set and clear various bits and change various settings. That allows you to avoid having to do, read, modify, write operations, which has a potential for, if you have multiple processor threads, you have to synchronize between those. So by using these atomic commands to set and clear, enable and pause bits and whatnot, this is going to make dealing with the queues a lot easier when we have multiple ports associated with each scheduler. So I went ahead and implemented that in a way that it'll work with multiple ports. And then I also just as of a couple days ago came up with a new method for tracking the queue active state. So previously I had this complex method involving keeping track of a linked list of all of the outstanding transmit operations. What I realized is that there was a much simpler way of doing that using a generation ID. So I went ahead and converted everything to doing that. And then I also realized that we only need to report the failed transmit operations to the pipeline, because that's the only time we need to take any action in terms of, disabling, or not disabling, but, marking a queue as inactive and descheduling it. Since we only need to worry about the failed ones and not all of them, since we're not doing this linked list thing, this reduces contention for the internal pipeline, because we can basically just drop those transmit status reports. And I also made a bunch of improvements to the pipeline itself to support a higher throughput. So previously I had a bunch of logic for like detecting hazards if multiple things were trying to access the same queue, that you'd have to wait. I came up with this read data override setup Previously when I was doing the upgrades to the queue management logic. So this basically eliminates the need for all of the hazard detection logic because you can just use the read data override to replace the read data that would have been stale with the latest data that would be written back into the memory. So this means that the scheduler pipeline can achieve a much higher throughput. I also added a FIFO to drain the pipeline for the transmit requests that it's generating. And the upshot of this is that the scheduler can now generate one transmit request per clock cycle, at least until you run out of flow control credits. And previously, the best you could do is one transmit request for every 2 clock cycles, because I think it was even worse than that. But the best you could do is one for every 2, because you'd use 1 clock cycle to issue the transmit request, and then you'd have to spend another clock cycle handling the transmit completion later. So since we don't need to pass those transmit completions through unless the queue runs empty, then that is going to improve the performance. So yeah, unless you have a lot of queues that are becoming empty or a lot of doorbells from the driver, the scheduler can now generate one transmit request per clock cycle. So that's huge, and that's definitely an important component in terms of being able to use one scheduler module for multiple ports. So yeah, just a couple more details on the active state management. So the scheduler needs to do a couple of things, right? It has to generate transmit requests for all of the packets. That's kind of the starting point in the whole transmit process. In order to do that, it has to know which queues actually contain data, so it's not, wasting cycles by trying to send stuff that doesn't actually exist. The scheduler doesn't actually have direct visibility into the queue state, so it has to track the state indirectly. So it gets doorbells from the queue management logic whenever software enqueues information into the queues and updates the producer pointers. And when it receives a doorbell, it has to set that queue active and potentially schedule it. When transmit operations fail, that indicates that the queue is now inactive, that doesn't contain any data. So the scheduler has to set the queue as inactive. But since the scheduler can issue, well, the transmit requests, they don't complete immediately. They take several cycles, and the scheduler can have multiple of these in flight at any given point in time. So the question is, what happens if a doorbell arrives at the scheduler while there's multiple transmit operations in progress? Well, the scheduler has to be able to ignore operations that started before the doorbell, even if they complete with a failure after the doorbell, because, that's those operations would be associated with, whatever the queue state was before the doorbell. They wouldn't necessarily reflect whatever was in queued. So you need to have some way of tracking that and ignoring those operations. So the original method that I came up with was relatively complicated. I had a linked list of all of the outstanding operations, and then as they completed, they would be removed from the linked list. And when a doorbell occurred, it would be marked on the last operation for that queue. Well, if there was one. And then eventually that would work its way to the front of the linked list, at which point the queue would be rescheduled. But this is kind of complicated to maintain these linked lists. It requires a bunch of additional logic. It requires a bunch of distributed RAM and whatnot. But what I realized is that, well, if I just assign a generation ID that starts at 0 and then we increment it every time we get a doorbell, what we can do is just ignore the status response if the doorbell doesn't match, right? If it does match, then it's current. If it doesn't match, then it means it's stale and we can ignore it. And this means that I can remove the entire operation table, all the logic associated with that, and we don't need to do all of the additional complexity of managing these linked lists. And so I went ahead and implemented this, and it works just fine in the hardware. So I guess I've already kind of gone over how the generation ID works, but yeah. So I'm not going to go over this in more detail, but yeah, it saves a fair number of logic resources, and it also improves the timing performance by not having all, async distributed RAM reads inside of the scheduler. So pretty significant improvement. And now that I have this working, then I'm in a very good position to get the last couple of pieces I need for the multi-channel scheduler support. So just a quick summary on the status. Things that I've done: single channel internal flow control, queue control commands, the new generation ID for active state tracking, the improved pipeline and pipeline throughput, improved scheduler throughput, and things that I have left to do are the multi-channel flow control and the multiple ports and TCs. So hopefully within the next week or two, I'll be able to get that polished off. I think once I have all this working, I'm going to do another push to the main upstream repository. So that'll be a pretty good checkpoint, I think. All right, so what else do I have here? So while I was working on the scheduler, I was thinking of a couple of other things kind of in parallel. So right now, the scheduler, every transmit request that it generates results in one packet being sent, possibly, or none if the queue is empty. And this basically imposes a very strict limit on the number of packets per second that you can possibly send, right? Because if you're running at a 250 megahertz internal clock rate, the maximum you can possibly send is 250 million packets per second, just based on what the scheduler can do. And it also complicates things in the transmit engine because that's all handling just individual packets one at a time. But if you have a lot of small packets, then this is potentially going to be a significant impediment to the throughput. So what I'm thinking about doing is changing the scheduler requests from, just a single packet per request to having the scheduler provide basically a byte budget and a packet budget to the transmit engine. And then the transmit engine can send as many packets as it wants up until it hits that limit. So the nice thing about this is if you set the packet budget to 1, then it's exactly the same as the current behavior. But if you set it bigger, then you might be able to get higher performance with small frames. So that's one thing that's kind of interesting about Ethernet frames is you can have a huge range of frame sizes, right? You can have really small 64-byte frames. You can range all the way up to like 9 KB MTU jumbo frames. Having the scheduler be transmitting 1 packet per transmit request, that doesn't necessarily work all that well when you have some 64-byte frames and some 9 KB MTU jumbo frames. That the fairness doesn't really work out all that nicely. So yeah, if we can have this code for multiple packets, so you can send like 10 small frames or 50 small frames or something instead of just 1 frame, then this is going to open up some opportunities for really cranking up the performance. The other thing that I was thinking about as well, other NICs do this on some level, is support for basically packet ring buffers. So right now, all of the communication with the DMA engine, it involves descriptor rings, but the problem with descriptor rings is you have to go read the descriptor and then go read the packet data and then send the packet data, and all the packets. With the way the Linux kernel manages packets, all the packets have to sit in their own little blocks of memory. But this isn't necessarily the most efficient way of doing things because you have all these additional PCIe reads and writes and whatnot. So instead, for higher performance, it might make sense just to put the whole packet in the ring buffer. And this, I think, makes a lot more sense if the packets are very, very small. If you're doing lots of really small packets, it's kind of the only way to get performance anywhere near line rate. Otherwise, there's just too much PCIe overhead. And this could also be kind of combined with, improving the descriptor handling performance. Like if we make the descriptor handling components actually capable of handling full-size packets, maybe we could use that same subsystem for everything. It's still a pretty preliminary idea at this point, and it's not really going to help all that much, I think, with the operation with the Linux kernel driver, but it could potentially significantly improve performance with DPDK. Now, I know other NICs do similar things because anything that can do 100 gig line rate with minimum length frames is going to have to do something like this. So Mellanox cards support this to some extent. if you go to any listing of DPDK benchmarks, if a NIC can do line rate 100 gig with minimum length frames, then they're doing something like this internally. So it makes sense, I think, to try and figure out how something like this might be implemented in Corundum. Maybe as an option, you can turn it on specific queues if you want, possibly. I'm not sure at this point exactly all of the changes that we require to make this work, but it's one of the things I'm mulling over as a potential thing to do going forward in terms of something that could significantly improve the performance. So I think that rounds it out for the architectural changes that I'm thinking about. Moving on to the application section pass through from MLE. So the application section pass through, the idea is that for certain more customized applications, you might need to connect additional wires, pass through additional parameters down into the core of the design or into the application section. So the guys at Missing Link Electronics put together a pull request to add some macro magic to support this. Unfortunately, the more magical part of the macro magic doesn't work on older versions of Avado, but it does work in the simulator. And I think reworking that to work with older versions of Avado shouldn't be all that difficult. It just requires a little bit more duplication in the the header file that defines all the ports and whatnot. But since it does work in simulation, I went ahead and merged it in to my development repo, and we can potentially make some modifications and updates to this going forward if as necessary. I also added some test benches so we can actually test and make sure that this pass-through is doing what it's supposed to do. So that's the current status of that. I think at this point that's not going to call it done, but it's basically done. We might just need to make some adjustments to the header file that you need to define the macros to make it work with other versions of Avado. All right, and then the Corundum testbed, I guess I announced last time around that it's basically operational at this point. So if people have ideas of stuff they want to run on it, talk to me on Zulip, and we can arrange access to that. So I have remote access set up. I have, I guess right now I only have one development machine hooked up, but I've got a couple of the big high-tech global FPGA boards. I've got a couple of packet switches. I got the network tester. I got the optical switches. Everything's all operational. Yeah. So if anyone has any questions about that or is interested in using it, let me know, and we can go from there. I think this rounds out my my status updates for today. So if anyone has any questions or comments, go ahead and fire away, or other stuff that you want to discuss. I guess we don't have too many people on the call right now, so maybe there's not much to discuss.
Just to say that very nice work, Alex. You have done a lot of things, I think.
Yeah.
So
it's been an unusually productive month, I think. some of the previous status updates, I'm like, I think I've probably presented the same thing like 2 or 3 times in a row, but okay. I think I don't know. There's advantages and disadvantages to doing things, doing the meetings every other week and doing them once a month. It's like, feel like once a month, okay, I actually have some more substantive stuff to report. But I don't know, maybe this time around we could have done with one in the middle, so I didn't have as much to report in one shot. But well.
I'm not sure if I'm audible, Alex.
Yeah, I can hear you.
Yep.
What's up?
So I have a very basic noob question to ask.
Sure.
So in the paper, we talk about multiple interfaces, right?
Yeah.
And there is a SRIOV support. So
Well, right now there
which is
actually
not
isn't. I've been thinking about adding SRIOV support at some point, but I just haven't had the time to work out all of the details for that.
Yes, but my question is, what's the difference between implementing an SRIOV support or providing this multiple interfaces as part of the Corundum design. So is it a difference? Would it provide?
Right.
So
So
basically,
SRIOV,
I'm
yeah. Right. So SRIOV is basically a way of enabling multiple drivers to connect to the same hardware design at the same time. So basically the way I've been envisioning how SRIOV would work is that all the drivers would connect to the same interface logic, but there would be basically some logic to keep track of what virtual functions are allowed to access each queue. So there would be some enforcement of that. But otherwise, it would basically act normally, right? Basically for SRIOV to work, you have to have multiple virtual functions, and each one has to be able to access the core NIC data path. So my plan for SRIOV support is to basically add the VFID through various internal components. So when one of the virtual functions accesses the bar, then it's only going to be able to access resources that have been configured for that particular VF. And it's basically only going to be queues. The VFs are only going to be able to NQ and DQ stuff. They're not going to be able to access any of the other core components. That'll be managed by the kind of master physical function. And then all of the DMA operations will also have to be associated with the VF such that they hit the right portion of the system address space and whatnot. So they're kind of tangential, I suppose.
So how is it different from the interfaces as mentioned in the paper?
Well, okay, so the interfaces in hardware, that basically corresponds to one interface corresponds to one set of queue management logic and schedulers and everything else. So if you have two interfaces, then you have two completely separate sets of queue managers, two completely separate sets of schedulers, two completely separate sets of, logic resources for the ports and FIFOs and everything. And as of right now, there actually really isn't much distinction between the separate interfaces. They're not exposed as like separate PCIe devices or something. The driver just registers two net devices, one for each interface. But the idea is that since all of that logic is separate, you get good isolation in the hardware between the two.
Okay. Thank you.
Does that make sense?
Yep. That yeah.
But yeah, I guess that's actually, that aspect of the design is something that I've kind of been rethinking a little bit, because as I work to improve the queue management logic and the scheduler logic and whatnot, I've been trying to figure out, okay, does it even make sense to support having multiple interfaces? Or should we just kind of roll it all into one block and then leave it up to the driver basically, or some other software component to divvy up the resources basically and accomplish the same thing without having to have as much duplication in terms of the actual logic on the device. There's advantages and disadvantages to each approach. So
But it makes sense in the cloud environment, right? Because it will really not make much overhead on the software side. So you won't really need to virtualize the interface in case of multiple VMs.
you wouldn't need
If
to?
you are, yeah, you wouldn't need to if you have SRIOV support. So practically, the virtualization will be auto-handled. That is what my understanding is.
Well, right. I mean, SRIOV is what allows you to handle multiple VMs connecting to the same hardware, at the hardware level, instead of needing a hypervisor or something. So so I guess it's a question of, where are you doing the virtualization, right? With SRIOV, you do the virtualization in hardware. Without SRIOV, then you have to use a hypervisor or something to do the multiplexing. right?
Yep.
Yeah. Yeah, at some point it would be cool to have SRIOV working. I guess, yeah, so the other thing that SRIOV needs is actually, the hard part is in the receive direction, is somehow you have to make sure with the incoming traffic that it gets sent to the correct VF. Right now I don't have a good solution for that.
But then do you have any ID association to it, right? You have an ID associated because only the VM that is using a particular VF has the access to that VF. And in this case, hypervisor.
Well, right, but I mean, you basically need a a network switch or something equivalent to that to figure out which queue to route the packet to, right?
Right.
Because with a regular NIC, you don't necessarily have to, you can just do RSS across all the queues and it works. But for SRIOV, you have to potentially check multiple MAC addresses, right? One MAC address or IP addresses or whatever per VF, and then route the packets to the correct queues in accordance with that. So you need some sort of flow steering or something else in the receive direction. So I don't have a subsystem for that right now. After implementing something like that, then it would actually make sense to consider adding support for SRIOV. But without that, yeah, you could have it so multiple VFs can own, or so different VFs can own different queues. But if you're just doing RSS across the queues, it doesn't really work. Are you interested in SRIOV, or are you just asking general questions?
No, so yeah, I mean, I've been working on it. I'm not working exactly on the SRIOV part, but I've been, because this fancy NICs comes with SRIOV support, not SRIOV support, so things like that.
Right. Yeah. Yeah, it's something I'd like to implement in Corundum at some point. I just haven't had the time or the application for it. Yeah, it's like basically if I have the need for a particular feature, then I'll find the time to work on it. But for SRIOV, yeah, there's a lot of groundwork that needs to be laid. It's possible that once Carlos has his switch with the route computation logic working, that could potentially be a basis for SRIOV support. We can bring that in as an embedded switch, or some subset of that, then that'll form kind of the receive side, and then we can connect that up with SRIOV support on the Corundum side. Not sure at this point. That's probably still several months out at least.
Yeah, but I think it sounds good.
Yeah, that was kind of one of the original motivations for, well, let's build a packet switch because we can make it both a standalone thing and hopefully integrate it into Corundum as an embedded switch. So
right.
But still got a lot of work to do before that point, unfortunately.
Just out of pure curiosity, I didn't know about SRIOVs, but I took a look, and if the different virtual machines access the same NIC, do they share the same MAC address, or can you define a specific MAC address by virtual machine?
Right. So my understanding is that you would have to set up different MAC addresses for the different virtual functions, right?
Okay.
For SRIOV, because otherwise, how are you going to route traffic to one VF or another?
Yeah.
So this is the one thing that I tripped up on the last couple of times I thought about SRIOV support. I'm like, oh right, but each one needs to have its own MAC address, and you got to look at the MAC address and route things appropriately, and potentially broadcast things to multiple SRIOV VFs.
Yeah, sure.
And,
because if you receive a multicast packet,
and the
you
other
have to
thing, too, is that the VFs might need to talk to each other, right? So some packets that you might send out of a VF wouldn't even leave the NIC; they would just zoop into a different one. So it,
yeah, talk to each other by the network. Okay, yeah.
Yeah,
Okay.
yeah. It's basically
Yeah,
for
that's crazy.
SRIOV to work, you have to have an embedded switch that can do a bunch
Yeah.
of routing inside. Otherwise, yeah. So it's like, yeah, okay. It's one thing to add it to the DMA engine and to add it to the queue management logic and whatnot. but there's no point in doing any of that if you don't have an embedded switch or something that gives you kind of an equivalent level of performance.
Okay, so
I think
that's on Carlos.
right, yeah. Well, I mean, it might make sense to take a look at some of the at what existing NICs do for SRIOV support and see if maybe there's some sort of a, you know, subset of a switch that could be implemented that would be a lot simpler. I don't know. My guess is it's probably going to be like, yeah, we'll just put the switch on there. That's going to be the simplest thing. But it's possible there's something simpler that could be done. Also, Corundum doesn't really have any support for any kind of flow steering or anything like that, where you can explicitly specify send packets that match these characteristics to this particular queue. You know, that would be potentially a useful feature and could be kind of a basis for, you know, some of this forwarding capability with SRIOV, but, you know, we don't have anything like that in Corundum right now. So,
Okay, interesting.
but there are actually pretty comprehensive data sheets available for some existing NICs, like the Intel, the 82599 NIC, I think supports SRIOV, right? It's got PFs and VFs, and they actually have register definitions for everything. So, you know, if I had some more time, it might make sense to sit down and kind of go over that with a fine-tooth comb and figure out, you know, what the functionality looks like there in terms of, you know, how is it handling the flow steering and whatnot. Both in the receive direction and then also in the transmit direction, figuring out what packets might need to be looped back to other VFs and try to see if, okay, is there something relatively simple we could do? I don't know. I haven't had time to look at it. But if somebody's interested in making SRIOV work in Corundum, that might be a good place to start. Let's do something similar to what I did with the Mellanox driver in the first place. Just use existing parts kind of as a reference to figure out, you know, what does the hardware need to do for this functionality to work. And also looking at device drivers makes a lot of sense too, because if you are going to implement the functionality in the hardware, you're also going to have to write a driver for it. So figuring out how that connects to the operating system, what tools are used to configure that, what the APIs look like, you know, that's also quite important to look at and have some understanding of. All right. Well, does anyone else have any questions or comments or things you want to discuss generally?
Just the last question by pure
Sure.
curiosity also. The Corundum DIG, does it support natively to be at different network speed?
Does the
Or
what?
yeah, does it support its MDX? I think I don't remember the name of the technology, but to adapt the speed function of the device it is connected to. For example, if I plug a device which is a gigabit Ethernet on the Corundum NIC,
Oh,
will the
so
speed be
like
adjusted
auto
automatically?
negotiation?
Yeah, auto negotiation. Sorry. No,
Right.
yeah,
So I
okay.
think right now we don't have any support for auto negotiation, but I have been looking at a couple different aspects of just kind of manually configuring to run at different link rates. So right
Okay.
now, all of the Corundum 25G designs, or at least on Xilinx devices, they can be dynamically configured between 10 gig and 25 gig on a per port basis. So
Okay.
um, you know, if you have say a board with two QSFP 28s, you know, you
Yeah.
can put any of those 8 lanes at either 10 gig or 25 gig at runtime.
Okay.
Because it's, yeah, you just switch to a different QPLL basically on the transceivers.
Okay.
Other line rates are potentially more complicated to support, but possibly doable. As part of the switch stuff that Carlos is working on, we've been trying to figure out how to support dynamic switching between 100 gig and 25 gig, right? So either you could run 4 lanes bound together at 100 gig, or you can split them apart and run that as 4 separate 25 gig links. So this is some of the motivation for being able to run with multiple ports is, okay, well, then we might be able to actually split between, well, and all the dynamic allocation and whatnot is then, okay, now we might be able to split at runtime between a single 100 gig port and 4 25 gig ports.
Okay.
So it's like the devlink support allows you to split ports, or at least gives you an API for port splitting. So you can use the user space tool to tell it to split the port. So that's how it works at the operating system level, but then how do we do it at the hardware level? Basically, that would be adding logic to reconfigure the transceiver registers and then also switch between using the CMAC and using 4 parallel 25 gig Macs. For running at lower speeds, you have to actually switch out or modify the Mac logic in some way. So I know we definitely have people ask about gigabit per second support. And
Yeah,
I know a
that's
lot
the
of
point.
the White Rabbit stuff runs at 1
Yeah.
gig.
Yeah, yeah.
So I guess last summer I actually put quite a few cycles into this with Carlos, trying to figure out what we might be able to do to support gigabit operation. And I actually came up with a few ideas that we need to think about at some point. So the big problem with gigabit support is that the CPLLs suck. I don't know. I don't know
You
what.
can use the QPLL, no?
I'm getting to that.
Okay,
I'm
okay.
getting to that. The CPLLs suck. Somebody at Xilinx decided to save like 5 transistors and not implement all of the very many divider settings. I don't know if you've looked at the data sheet for the CPLLs, but they have like 12 possible divider settings between. If you look at all the different divider stages, there's like 12 ways you can configure it or something. That's
Okay.
it. So it's very limited in terms of what reference clocks you can use, right? If you almost need to pick the reference clock based on what link rate you want to run at. So if your reference clock is 156, then you can run at 1 gig. But if it's 161, then you can't.
Yeah,
You
okay, I
can't
see.
configure the CPL to do that. And most of the boards that I have are 161 or 322. They could have fixed that by adding a couple of more divider settings, but that would make too much sense. So it's like, come on, guys, really? So yeah, you can't use the CPLL. Now, you asked about QPLLs, right?
Yeah.
10 gig versus 25 gig. It's a 2.5, it's a difference of 2.5x, right? So
Yeah.
you can't use the same QPLL for 10 gig and 25 gig. You just can't. You'd have to run it at like double the. You'd have to divide by 2 for 25 gig and divide by 5 for 10 gig, and you can't run them fast enough to get a divide by 2 for 25 gig. So
Okay.
one QPLL is for 25 gig, one QPLL one is for 25 gig, one is for 10 gig. How do you get 1 gig?
But what we do in the switch is that actually we have oscillators on the reflux, and we can set the frequency of the oscillators, I guess, with an external PLL. So I think it would be possible if you change the reflux frequency. Oh no.
Well, I mean, yeah, sure, but most boards don't support that, or a lot of boards don't support that.
Because if you stop the reflux, the MGT block will go crazy. I mean, it will crash. That's why it does not support that.
No, it's then there's a good number of boards that have fixed oscillators that can't be reconfigured.
Ah, sure. Okay. Yeah. Okay. I understand.
Yeah, like the XNIC, X10, and X25, it's fixed 161.
Okay.
You can't reconfigure it even if you wanted to.
Yeah.
So,
Okay.
So yeah, I came up with this crazy idea of well, it turns out that so gigabit runs at 1.25 gigabits per second. If you divide
Yeah.
that by 8, you get 156.25. Well,
Yeah.
10G also operates at 156.25. It's just
Yeah.
66 bits instead of 8, right?
Yeah. Okay.
Well, okay, what if you did some oddball oversampling? You leave the thing configured for 10G, but then you just spread out those 8 bits across the 66 bits. It'll work for transmit. It probably work really well for transmit. For receive, we're going to have to see and whether or not things work properly with a standard gigabit interface or gigabit link coming into a 10G transceiver. I think it might work, but you'd have to do basically kind of a software CDR to pick the correct 8 bits coming out of that thing.
Okay.
But that would potentially let you get a 1 gig link. Now, obviously, you then have to go write a slightly customized PCS to take this 8 bits per cycle and pull it out into whatever you need for 1000 base X. But in principle, it should be doable. And then I thought of an even more interesting idea is that, okay, let's say you do that. I don't want to have a whole separate gigabit Mac. Could I use a 10 gig Mac for gigabit? It should be possible, I think, to convert GMII to XGMII. Yeah, you got to kind of repack and shift things around. But
Yeah.
if you did that, and then obviously it's just like one cycle every 8 or 10 or whatever.
Yeah.
That should work. I've also been thinking about. So another thing that we'll need for White Rabbit is we'll have to run the transceivers with the synchronous gearbox instead of the async gearbox. So that means we'll run at 161 on the fabric instead of 156. And then we have this, not every cycle is valid kind of thing. It averages out to 156, but you have a couple of stall cycles in there. So that's going to have to be coordinated, through the stack. In the receive direction, it's not too bad because you can just add a valid signal that, falls all the way down. In the transmit direction, the setup that I've come up with for now is basically to kind of do a loop back. So near the transceiver, you'll generate a you'll have a state machine that follows what the gearbox wants to see in terms of the stall cycles and whatnot. That gets sent all the way up to the Mac probably, which will then turn it back around and then send it all the way back down to the transceiver. And this means that as you're configuring between different link rates or whatever, the PHY can modify based on what its internal gearbox needs to do to tell the Mac which cycles it can send data on.
Okay.
And then that hopefully would allow you to work for both gigabit and 10G.
Okay.
I think there's potentially a few odds and ends to figure out to get all the kinks worked out of it, but at a high level, it seems reasonable.
Okay.
It's
it's a good
obviously
news.
there's work to do, but it seems like it should be doable, and then that would support operation at both 1 gig and 10 gig and 25 gig. And I was also looking at there's a few other link rates that are possibly used, right? There was also 2.5G base X and
Yeah.
5G base R. So 2.5G base X is just basically 2.5 times speed of the 1G base X, and then the 5G base R is just 10G but at half rate. So
Yeah.
potentially those would be relatively easy to support. But then I took a step back. I'm like, does anyone actually use those rates? I don't know.
Yeah, I don't think so.
So I don't know if it makes any sense to waste any cycles on that, but potentially you could support that. So yeah, the idea is that you could have one kind of multi-rate module that could support gigabit, 10 gig, 25 gig, and 100 gig, and you could dynamically switch between the rates. And yeah, I guess there is some question of whether or not all this would work properly with the transceivers, at least with the 1 gig support, and whether it would work properly with White Rabbit. I mean, again, with the 1 gig support. So
yeah.
At some
But
point,
there's
I guess
some
we need to do
ideas.
some. At some point, I guess we need to do some experiments, kind of as a proof of concept, and just see if things are going to be well behaved with this oversampling technique. So now, Carlos, you said you were going to work on that, but I guess you probably haven't had much time.
I didn't have time during this last month, so yeah, I started doing some stuff, but yeah, I had to stop it to concentrate everything into the Switch. So.
Right, yeah, okay, that's fine. That's
yeah,
kind of what
it's in my to-do list, but yeah, of course, I don't know when.
Right, yeah. Yeah, because what I was thinking we could do, I mean, talked with Carlos about this before, is to take like the ZC102 board that has 4 SFP plus modules in there, and then you configure them with various combinations of 1 gig and 10 gig, and then either put a bunch of loopbacks in there or a couple of just short cables to cross connect the ports in pairs, and then you can run a pretty self-contained test. And I'm talking just about at the link level here, not even building a 1 gig PCS, but just doing PRBS at 1.25 gigabits per second, and make sure that everything looks reasonable. Because you got to get all the combinations of transmitting from a a transceiver that's properly configured for 1 gig to one that's configured for 10 gig but running at 1 gig, and vice versa, and so.
But yeah, SFP transceiver can change the rate, the data rate.
A lot of SFPs, they don't care about the data rate.
Okay, just a diode basically. So
yeah,
yeah.
It's more the QSFP 28s where you can run into problems because they have CDRs in there. Not always, but they can. And then the CDRs usually only work over a very narrow range.
Okay.
Or they work either over a very narrow range or at multiples. So if you take a 25 gig transceiver, you can run it at 12.5. That's fine. But if you run it at 10, you got to go in and poke a register to turn off the CDRs. This caused some annoyance when I was at IBM because I had a design working at 10 gig. It worked with the electrical loopback, but it didn't work with the optical transceiver. I'm like, what the heck? The 25 gig design works fine, but the 10 gig doesn't. I'm looking at the datasheet. The datasheet doesn't say anything about a CDR. But then, yeah, I was talking to one of the other researchers, and they're like, it sounds like there's a CDR. I'm like, datasheet doesn't say anything about a CDR. It's like, it sounds like this is a CDR. Like, okay. We contacted the manufacturer of the module, and they're like, oh yeah, there's a CDR. You got to write this register to turn it off. And we're like, oh, great.
A CDR basically.
Why doesn't the datasheet say that?
It's a PLL CDR, basically, no?
Right. Yeah.
I mean,
well,
it's
I mean, I
looking-
don't know exactly how the CDRs work in these things.
Yeah.
There's many different ways you can build CDRs. And some of them operate over wider ranges than others. But
Okay.
the ones that they have in there, I think, only work across a few hundred ppm. Xylem
Yeah, okay.
transceivers are the same.
So
they only work over a few hundred ppm.
Yeah, so they couldn't lock on the frequency which was that low.
This is
Okay.
just too far out of range. Some of the CDR chips that I've seen, either they can work over a very wide range, or they have some more complex algorithm for like detecting the data rate and then reconfiguring their internal PLLs accordingly. Yeah, I think there was one from TI that I looked at the datasheet for a while ago that basically it'll work at pretty much whatever data rate you run it at, and you don't need to reconfigure it. It'll just kind of figure itself out. So some modules might have CDRs like that, some don't. So yeah. And some of them don't allow you to turn off the CDRs, so they only work at 25G, which is annoying. but
it's only on QSFPs.
But generally, yeah, I've only had a problem with the QSFP 28s. Now, when you get up into the faster stuff like QSFP DDs, okay, that's a completely different animal.
Yeah. Okay.
Yeah, those are much more complicated. Yeah, with the QSFP DDs, there's a difference between 1 by 400 gig and 4 by 100 gig. The difference is at the PCS level, and because these things have, an internal PCS and they can reshuffle stuff, the format has to be right for it to actually bring up the link. Or, well, yeah, it has to match. So, yeah, those are less amenable to running at oddball rates. But that's actually a good question that I haven't really thought of until now. Is I don't know how some of these transceivers might affect something like White Rabbit. If you're trying to do the really precise timing, does any of the oddball stuff that takes place inside of these transceivers affect the clock and whatnot? As it's possible, for QSFP 28 and whatnot, it's probably fine, but for some of the QSFP DD modules, depending on how much stuff they're doing internally, if they're like inserting and deleting idle characters or something, they might not be forwarding the clock necessarily the same way that you have on other modules. I don't know. That's probably a whole different can of worms for another day.
Yeah. For now, we'll stick with the SFPs, I think. Classical ones.
Alex, if you have, just last question, if you have time. So, if you remember your U280 port of Corundum, right? So there was a satellite controller.
Yeah.
And so I watched the whole stuff, right? But I couldn't really understand. Did you do any configuration for satellite controller, or no? You didn't touch at all.
Yeah, so I think on yeah, so this is the part where Alveo boards are kind of annoying. So on all of the Alveo boards, the satellite controller thing basically gives you like sensor readings, voltage and temperature, and I think yeah, right. You could also read the pre-configured MAC addresses out of this controller. So the driver right now, that's all it can do. It just accesses the I think it's just the MAC addresses. Potentially that could be extended at some point to include the sensor stuff. Um, but yeah, for the time being, it just looks at the MAC addresses. Now, there are when you have the optical modules on there, like the QSFP28s, there's generally going to be an I2C interface for configuring the optical transceivers and also reading like, power levels and things like that. And controlling the CDRs that we were just talking about.
Yes, yes.
On the U200 and the U250, that I2C setup is connected directly to the FPGA. On most of the other Alveo boards, it's only connected to the satellite controller. And I think Xilinx has changed the firmware on the satellite controller a couple of times in terms of what it's capable of, in terms of what the interface is for talking to the optical modules. So I would need to look at what the current version of that is and figure out, what the process is for, sending a command to read or write a register on the optical module. But it adds a lot of additional complexity to do that. And since they've updated the firmware a couple of times, I would also need to figure out like how to update my boards and make sure that the MSP 430 on there is running the right revision of the firmware. It's a big can of worms. Oh, and the other aspect is that the driver right now is really only set up to do bit bang I2C for everything. So there wasn't really a nice way of even exposing the optical module interface via the little system controller thing. So
So
I think
you didn't have to configure anything. It
yeah, you
just
don't
worked
have
out
to.
of the box.
It's there. If you want to talk to it, you can. If you don't talk to it, it should just work, right? And unless you need to talk to the optical modules or something. So does that make sense?
Yep, yep. It was very helpful as well. It gives and also it gives a little bit more insight into technical aspects.
Right, yeah. That whole system controller thing is such a Rube Goldberg setup. Do you know what a Rube Goldberg machine is?
No,
It's
too
the
too
thing where
young
you
for
have
that, I
like
guess.
a marble that rolls down a track and knocks something
Mhm.
over, and then that knocks something over, and you know what I'm talking about, right?
Mhm.
Built out of a
Yeah.
bunch of
Yeah,
junk.
yeah,
Yeah, it's a Rube
yeah.
Goldberg machine. So it's kind of like that, right? If you want to access the the system controller, right? You have the driver that will talk to the the CMS IP core, which is a microblaze running software. The microblaze will then go send a command via serial to the MSP 430 board controller. It's like, how many different links in the chain do we need here for this stupid thing to work?
So I'm sorry. Just last thing. So the other day I was working on the microplace, and so in a microbase there is over axis, if you want to confirm whether the write is successful or not, what it does is it sends a packet for the write and then issues a read on axis.
Mhm.
Whereas it can also use the response, which actually tells you whether your transaction was successful into writing or not. Axis supports that. So
Right.
they could have just used that rather than just using issuing another read to the memory.
Wait, for what?
So let's say I have so if I'm issuing a write to the memory from microblaze over axis,
Yeah.
and the request goes to interconnect and from interconnect to the memory, and it will give you a response whether the operation of writing was successful or not.
Right.
So And you would know whether your write was successful. But what microblaze does instead is it issues a read for the same memory address and confirms if the value that you have written was exactly the value that you read.
Oh, wait, so you're talking about code that you saw somewhere that runs on the microblaze?
Yes, it's a driver, Axie driver.
That seems strange.
It does that. I opened up the source code of the driver and it does exactly that.
Yeah, it sounds like somebody that doesn't understand how computers work, basically, to be honest, because the problem with AXI is that the read data is not necessarily going to be the same as the write data, right? Depending on what you're accessing. Like if you have a MMIO registers, it's possible that it's always going to read a 0, right?
Yeah.
So that kind of method, it only makes sense if you're actually accessing memory. And at least in the case of doing stuff on FPGAs, I think that's a very poor assumption to make. So yeah, I don't know. Oh, Quentin's got to clear out of here. All right. See you later, Quentin. Yeah, so I don't
See
know
you
why
guys.
they implemented it that way.
Yep. So that was funny. Like they could have done it very easily. They had the support for it. All they had to do is just read the response from the Axie.
Right. Well, I also don't know how the how that response channel is handled inside the core. Maybe there isn't an easy way to get access to that. Because a lot of CPU cores, you know, they won't expose very many low-level details about the bus interface, right? They can just issue read instructions and write instructions. So it's common to use read operations like that for timing purposes, for serialization purposes. And I've done it myself. You definitely have dummy reads in the Corundum device driver in various places for a similar reason. It's like you don't have any feedback as to whether or not the write actually completed. So, and you don't necessarily want that, right? You might want to be able to issue a bunch of writes and then not have to wait for them to complete. So it's possible that the microblaze is just kind of ignoring that write response channel so it can issue a bunch of writes. With the reads, obviously you got to wait for it to complete before you can do anything. But for the writes, you don't necessarily have to. So it's possible they don't. But yeah, I don't know why you would actually check the read data if you do that. That doesn't make sense. Because all the dummy reads that I have, it's just a read, and then it just discards the data. I guess the other thing that makes AXI a little bit weird is that the read path and the write path are totally separate. So you could potentially issue a read and a write at the same time and have the read complete first.
Yeah.
Instead, as opposed to other protocols which enforce a more strict ordering.
Yeah, but it depends on the consistency model that you're following.
I mean, yeah, I guess it technically it does, but I don't know how AXI even enforces ordering between reads and writes. Is that implemented in the interconnect or something? I don't recall there being any linkage between the TX or between the reads and the writes.
I'm not sure.
Yeah. Yeah, I know PCI Express is totally different. PCI Express orders, well, doesn't order everything, but it does have a defined order between the reads and the writes. So that's actually something that I might need to take a look at again in the in my PCIe AXI Lite code to make sure that it's ordering things properly.
So
Because
the function
yeah,
the function name is Excel _ secure out. So those are like secure ones. So basically they check it's a secure out because it makes sure that if you have written what you expected.
Oh, okay. So that might be a slightly different story than just a normal operation. So maybe
Why,
you
sir?
only need to use that when you know that the AXI is going to be well behaved.
Yeah.
Yeah, I can't think of really when you would need to use something like that as opposed to just a normal operation. But it sounds like they're trying to do something specialized with that.
Mhm.
Anyway,
Thank you.
yeah, sure. Anything else to discuss? I guess Quentin had to clear out of here, so all right.
Nothing from my side.
Nothing from Carlos. All right. Well,
No.
I guess we're good for today, and we'll see you guys next month or next week if you want to hear from Carlos and the switch he's been
Next
working
week.
on.
Okay,
So
thank you very much,
Carlos,
Alex.
So you have that thing working with the MAC address learning on 3 ports, right?
Yeah, this week I had put some work on making it happen with 9 ports, but I'm struggling again. If you remember last summer, so I'm trying to do
Timing
yeah,
closure.
yeah, you are like 0.2 something, and Pivado is messing everything up. I mean, it's not everything
What's
doing the
new?
same thing. Yeah,
Yeah.
trying to use a Laguna register and so on, but sometimes I don't know why it doesn't use all it should use. So I'm trying to force some of these with more constraints. Yeah, we are at this phase. Yeah,
Well,
I
if
started with
anything, you're getting
something
very
like
good at wrangling Vivado. So
yeah. I think it's just finding what it wants to yeah. It's just a question of time, I think.
right. All right. Well,
Hopefully soon.
we can get the bottom of that and get that working, and that'll be pretty sweet.
Yeah. Let's see next week if I have good news.
All right. Sounds good. Well, good luck with that, and we'll talk to you next week.
Yeah. Thank you for the meeting. Very interesting.
All right. Thanks for tuning in.
So, see you.
Back in.
Thanks.
Bye.